Good morning or good evening, everyone. Welcome to this class, Input Motions for Site Response Analysis. So this class will help you understand the requirements for how to select the base ground motions for the site response analysis. So before I talking about how to select the base ground motions, I'd like to talk about the difference between the site response analysis. So basically, section 21.1 and the ground motion hazard analysis, basically section 21.2. The commentary of chapter 21 indicates three approaches for site-specific ground motion analysis. They are listed on this slide. So the first approach is a PSHA. So PSHA stands for Probabilistic Seismic Hazard Analysis, and possibly DSHA if the site is near an active fault. DSHA is a Deterministic Seismic Hazard Analysis. So when the site is near the active fault, typically the deterministic cap will control the plateau seismic node, so which is the situation in California. So the first approach is used to compute the ground motions for bedrock or stiff soil condition. So typically you cannot use this approach for site class E and F. Based on the commentary, there are two options for this approach. The first one, you just compute the bedrock motion from the PSHA or DSHA. Then you site coefficient FA, FV in section 11.4. Then you basically adjust the SS1 developed from your own PSHA on the DSHA to the ground surface. Most of the time, you cannot use this option because the reason you want to do the site-specific ground motion analysis is because FA, FV, they are not available in the tables in the section 11.4. So the second option is you can compute the response spectrum at ground surface directly from PSHA and DSHA. This approach, neither require you use attenuation equations or the ground motion prediction equations. Based on the location, there are two major set of equations. One is for the western U.S., another one is for central and eastern U.S. So this approach typically needs a lot of effort. For the PSHA analysis, you need to identify the active faults around the project site. You need to determine what kind of attenuation equation you need to use, based on the fault type, either strike slip fault or normal fault or reverse fault. Then, you need to determine what kind of weight factor from the different attenuation equations and what are the contribution weight factor for different faults. So eventually you will develop a tree they call as a logic tree to calculate the overall seismic response. And right now, as we know, the ground surface motion is a risk base. That's why we call the MCER. The R represent the risk. So you need after you done the PSHA, you need to consider risk factor. What kind of risk factor apply at the seismic demand at different periods? So this add another complexity to the problem. Also, this type of analysis is not easy to get through the peer review because people have different opinions on what are the active faults, what kind of weight factor used on different equations. Even, they have a different opinion on what a attenuation equation you should consider. And also, finally, you may not get much benefit from this type of analysis to reduce the seismic loading because attenuation relationship you used are based on a lot of site response analysis. So basically, those equations are developed by enveloping many site conditions. So theoretically, they are not site specific. So typically, I won't recommend this approach unless client requests. There is no fundamental difference between the approach 2 and 3. Approach 2, basically, you need to run your own PSHA or DSHA to determine the bedrock motion. Then after that, you run the dynamic site response analysis. Approach 3, you can use the bedrock motion developed from the seismic map, and based on that, you run the dynamic site response analysis. Note, the USGS seismic maps are developed through rigorous PSHA, DSHA with considering risk factors. So basically, it's definitely fine to use USGS seismic map to determine the bedrock spectrum because they already consider the PSHA, DSHA, at the same time the risk issue. So the approach 3 is an approach I typically recommend for the site-specific ground motion analysis, and the following classes are based on this approach. Again, we see this slide in the class 2. These slides give you the components needed for the 1D site response analysis. Certainly, you need the input motion at the rock base, which will be covered in this class. And you need the soil profile and properties. And lastly, the soil model. So let's look at the exactly requirement from ASCE 716 for the base ground motions. So I won't read this for you, but there are several things I highlight here. Certainly it allow you to use a section 11.4.6 to determine the bedrock response spectrum. So that is you use the USGS map directly, or you can use the approach in the section 21.2. So basically, you do your own PSHA, DSHA to determine the bedrock response spectrum. So basically, that is approach 2 in the previous slide. So it's defined as class B. So basically, we call the BC boundary. So that corresponding the shear wave velocity 2,500 feet per second. So that's where the location will determine where is the rock for your soil profile. So then after that, at least 5 motions, 5 recorded or simulated horizontal ground motions should be selected for this analysis. And the ground motion are selected based on the magnitude and fall distance associated with the MCR ground motion at the project site. And finally, for the selected time history, you can either scale or do spectral matching. On average wise, regardless you have 5 or 10, you average the response spectral input motion. They should be approximate to your rock response spectrum over the period range of significance to the structure response. So this slide shows how to determine the bedrock response spectrum. So this figure just show the approach. You use the USGS map directly you get SS S1. So for this case, the SS is 1.5 G and S1 is 0.6 G. So then you use the FA and FV based on your site class. Then you can, basically this is site class B. So FA, FV, that will be 1.0. Then you will determine the Barak spectrum based on the section 11.4.6. And this approach is indicating the section 21.2. So basically you need to run your own PSHA for the bedrock, then the DSHA for the bedrock, and the site-specific spectrum, MCR spectrum, will be the lesser of two. So the red one will be the site-specific spectrum from the approach 21.2. So for this example, this approach give you a smaller rock spectrum at period range from roughly about 0.2 to 0.7 second. After that, you need to find the earthquake with a similar magnitude and fault distance associated with the MCR bedrock spectrum at the project site. Typically, there are no recorded earthquake event near the project site. So you have to search existing earthquake database to find those events with a similar magnitude and fault distance. So the question is how to determine the magnitude of fault distance. So we typically run analysis called as de-aggregation analysis. So this slide shows an example of de-aggregation analysis. The de-aggregation analysis basically it segments the contribution of different seismic sources of fault. So for this example, you can see there are two major sources for the seismic demand. One, they are the local source or local force. They are very close to the project site. It's about 15 kilometers away. And another, they are probably much bigger fault, but they are further from the project site. They're about at least 85 kilometers to the project site. So the local fault generate a small earthquake, magnitude about 5 to 6, and a big fault. It generates much bigger earthquake, magnitude 7.5 to 8. And this each bin on this figure represents the contribution to the overall seismic response in percentage. So at the same time, this analysis also provide the mean value, basically the mean value from all sources. So this is the mean magnitude, that's 7.11, and also this R is a mean fault distance. So for this case, it's 71.13 kilometer. So basically, if you go to USGS, you click this link, go to USGS, you type your project location, it will automatically do the deaggregation analysis for you. One thing I want to remind you is the deaggregation analysis, they are different for different period. For this case, is for the 0.2 second period. So you also need to do a similar analysis for the period of 1 second. Then you combine two to determine a range of magnitude and the fall distance for the project site. So for this project, you can basically select the earthquake with magnitudes between the 6.5 to 7.5 and maybe the fall distance from the 50 to 90 kilometer. So once you determine the appropriate earthquake events based on the magnitude and the fall distance, you can get the input motion. However, most of the time, the input motion response spectrum doesn't match the target rock response spectrum. As shown on this figure at the right-hand side, the green dashed line, that's the response spectrum from the input motion, and the blue, that will be the target. The reason for that, because the rock response spectrum is a uniform hazard spectrum, but the input motion they are not uniform hazard spectrum. They just from lateral earthquake. So there are two approaches to make the input motion to match the target spectrum. One is the spectrum matching. So what they do, they just change the wavelength or the frequency component of the input motion. At the same time, they will scale the input motion to make it match to the target spectrum for each individual input motion. So as you can see, after this analysis, the red one, that's the matched motion, pretty close to the blue one, the target response spectrum. So there is a program which is a free RSP match, which can do this type of analysis. Another way is the simple scale. You find more than 5, a bunch of input motion. You apply a different scaling factor for each input motion. Eventually, you average all the input motion, then you get an average response spectrum. Like in this example, is as a dark black line. So then the red one is a target response spectrum. So for this case, after 0.1 seconds, so they are close match. Either way has pros or cons. The spectral matching used to be very popular because it's easy to do. The simple scale sometimes is can time consuming, very difficult. You have to, if you manually do that, you have to try different scaling factor combination. Eventually, you may not get the results as you desire. However, the peer center recently developed a tool that can automatically to do the simple scale approach. So actually, this example is from the peer earthquake center. So now this approach, simple scale, get more popularity recently. So as what I said, this is a peer ground motion database. So if you click this link, you can go to this website. So on this website, it provides 2 set of tools for select the motions. It depends on the location of your project. If your project in the western coast, you need to use NGA West 2 model. So you click this link. If your project in the Central and Eastern North America, then you use this link. So if you click the link, the instruction is straightforward. Just follow the instruction step by step. You can select the input motions for the site response analysis. I think one tip, this is important, just even the code, as what I mentioned in the previous slide, only require minimum 5 input motions. If you want to get a good results, do the simple scale using the simple scale method. Make the average response spectrum match the target spectrum well. My recommendation is better to select more input motion. For example, like 10 to 15 input motions. So when you have this larger set of input motion, it will be much easier to average them to match the target spectrum. And there are a lot of, in the later class, when I talk about site response analysis, some programs has a batch analysis capability that can run many analyses concurrently. So it doesn't matter you have 5 or 15, it just run as one batch analysis. So this ends today's class. Feel free, let me know any questions and comments. Thank you very much.